Okay, so this is what we defined last time. We said that we don't have to restrict our idea of measurement to just projective measurements. Rather, we can instead talk about this kind of an idea, which is called a POVM, which is nothing but a positive operator valued measure. Right? And the idea is that instead of a set of projectors, which is what you normally associate with a measurement, you now have a set of positive operators, positive semi-definite operators, which lie between zero and identity and which sum to identity, right? And we have identified a probability rule by which we can extract a probability distribution out of this. Like I said, this is a valid probability distribution because you can because these operators EI, so like I said, trace of an operator with a rank 1 projector or a pure state, right? This is nothing but the expectation of the operator in the state side, right? So now since the EIs lie between 0 and identity, their expectation values must also lie between the expectation values of 0 and identity, which basically lie between 0 and 1. So this property then says that this lies between 0 and 1, and you sum over the i's, right? I have labeled them 1 to n now. So sum over I, P of I, going from 1 to n is nothing but, we did this the other day, so you can check that this is nothing but 1. And this is a kind of if and only if statement, which follows from the fact that sum over EI should be identity, right? This is, like I said, often called a completeness property, right? This completeness property is satisfied by the projectors onto an orthonormal basis in a Hilbert space, which is why they give rise to a kind of measurement, which is the projective measurement. Now we're going beyond that and constructing this. The one thing that I did not tell you last time was I gave you the probability for different outcomes. I gave you a rule, let's say, for the probability of different outcomes. But what about the post-measurement state? Now recall that in the case of a projective measurement, let's say that you had a set of orthogonal projectors P1 to Pn. Note that these could just be projectors onto some orthonormal basis, for example, right, of this form, right? Okay, so in this case, now if, so corresponding to outcome I, we said that the state psi, and we rather looked at it as a transformation on the projector onto state psi, right? And we said that this goes to pi psi psi pi, but then we had to normalize this by the associated probability of the outcome, right? So this was the collapse postulate stated in a much more formal way. The simplistic way of saying it is psi collapses to EI. Okay. Now this is not just a fancier way of saying it, it's a more formal way of saying it. Because, what if your projector is some higher rank projector, for example, it's not just in the form EIS. You need a formal way of stating this in terms of the projection operator itself. Then the way you would say it is, think of the projection onto psi and how does that get transformed by the corresponding projection operators associated with the outcome I, right? And this, that when I write down psi like this becomes a matrix. Remember, this becomes an operator. So sandwiching this between the two PIs is basically because this is the operators act on operators by conjugation, right? So this is called acting by conjugation, that the PIs go on either side of the operator sign. Okay. Okay. Now, what is the corresponding rule here, right? So here, corresponding to outcome I, what is the post measurement state? Okay. So now, because the POVM is not really coming from a physical idea of measurement, right? In the sense of a Hermitian operator and its orthogonal projections and so on, there are actually several ways of associating the outcome state, right, with a given outcome. So the first point to note is that there is no unique association like the collapse postulate. Okay. The POVM is much more of a mathematical construct than a physical, coming from physical considerations, right? Physical considerations tell you observables, Hermitian operators, projective measurements, right? But we are just trying to extend the idea now mathematically, also because we're sort of probing the limits of information and distinguishability and things like that. So that's where the idea of a POVM comes from. But now there is no unique association of a post-measurement state like the collapse postulate. In fact, this depends. So this is the first thing to note. And the post-measurement state actually depends on how the POVM is physically realized. In other words, the apparatus. And in this case, the apparatus is technically often called an instrument. Okay, the instrument has a very mathematical definition in this context. We'll not get into that. That takes us into the realms of quantum foundations and all that. But I just want to note that this cartoon box that we draw here, right? And if this is the one that's realizing the POVM, the probabilities remain fixed, right? So the probabilities of the different outcomes remain fixed. Why does that remain fixed? That is associated with the set of positive operators that characterizes the POVM. But the post-measurement state is something that is determined by the nature of this apparatus or the instrument, right? So it is some general transformation which is associated with outcome I. The simplest or the canonical association that is often made is the following. So let me just write down what I call the canonical post-measurement state. And that association is as follows. So again, you take this projection onto psi. And now, corresponding to every EI, remember EI is a positive semi-definite operator. So you can associate the square root operator for this, okay? Because this is a positive semi-definite operator, which means that its eigenvalues are all positive. And remember, we discussed how you can define these functions of operators simply via functions of the corresponding eigenvalues. So this square root EI is simply an operator which has the same set of eigenstates as EI, but whose eigenvalues are the square roots of the eigenvalues of EI, right? So now this operator plays the role of the PI, the projection operator, in the case of the projective measurement. So this is the measurement transformation that's associated with this one measurement transformation that can be associated with corresponding to outcome I. And of course, this then has to be divided by the trace. Actually, the way you would normalize the state is to simply say trace of the same thing, right? Trace of square root EI, psi square root EI. But since trace is cyclic, so what happens? You can merge these two square root EIs and you get simply EI. So this indeed gives you the same probability association. So whether you think of this as normalizing the post-measurement state or as weighting it by the probability, it's the same. right? That's why it's a kind of canonical association, right? And this is a valid description of the post-measurement state. So either you can think of it this way. Let me just replace it by EI psi psi to keep it consistent with the projective measurement. Okay, so this is the post-measurement state associated with outcome I. Yeah, so like I said, there could be several such transformations that you define, and it doesn't quite matter because you see, for a projective measurement, the physical realization is very clear. It is the measurement of a particular observable. So if you realize a particular outcome, it has to collapse to the corresponding eigenstate. For a POVM, since there is no association with a physical observable as such, the post-measurement state is something that is dictated by the physics of how you implement the POVM. And this is a canonical association or the simplistic post-measurement state that you can associate with it. Okay. All right. So moving on. Now, what I wanted to do, taking off from where we left last time, is to ask about distinguishing non-orthogonal quantum states. Any questions so far?
Ma'am.
Yeah.
What do you mean by root of EI?
Yeah.
Because it is
So
a
this
matrix.
is what I said. So sorry.
EI will be a matrix. Root of EI.
Yeah. So EI is a matrix. The way I will write down this matrix is in terms of some set of eigenvalues of this matrix. Okay. In some orthonormal basis. Let me call this Fj. Okay. Right. This is a positive matrix, so it can be diagonalized. Correct? You agree?
Yes,
okay. Now square root EI is simply the same operator except with eigenvalue square root lambda I.
Okay. Thank you, ma'am.
So think of if you think of this as a diagonal matrix, since you can always diagonalize it with diagonal entries lambda 1 to lambda d, then the square root matrix is the matrix with diagonal entries square root lambda 1 to square root lambda. This is not the matrix with whose entries are all square roots of this matrix, by the way. Please don't make that confusion. Yeah, so square root EI does not mean you take the square root of every entry of this matrix EI. It is not that. You diagonalize it and then you take the square root of the eigenvalues. That matrix is what square root EI is. Okay?
Thank you, ma'am.
Yeah, sure.
Excuse me, ma'am.
Yes?
Ma'am, is there any formal way of arriving at this set of positive operators? I mean, why am I
Sorry, is there
asking
a formal way of?
arriving at this set of positive operators? I mean, why am I asking this is when we were discussing orthogonal projections, right? So let's say I want to differentiate between 0 and 1. So plus and minus. So I know that in a way, okay, I was taking two sets of I was working in a two-dimensional space, and I was looking, okay, it can be expanded in particular set of bases. This is the space that I'm working in. It has this dimensions, right? But here, here it is not that trivial to understand this. I mean, how many number of positive operators do I require to complete to be able to achieve the task?
Nice. No, that's a very nice question. So what you're asking is, what is the number n that I've written here, right?
Yeah, exactly.
Exactly. Okay. So if I'm in a d-dimensional Hilbert space, or if I'm talking about d-dimensional quantum systems, what should n be, right? Is there some optimal n? Is there some upper bound on n? Is there some lower bound on n, etc.? Right? This is how I would formally phrase your question. Okay. Now,
yes.
it turns out, yeah. So, it turns out that there is really no constraint on n. Okay. Unless you put some specific requirements. For example, if I say that n must somehow comprise only of rank 1 operators. Okay, so if I demand that my set EI, okay, so let me just make some remarks on this since the question has come up. I can put some references on this in Moodle because I mean, it's a very fascinating topic, POVMs and how to realize them and so on. But okay, so is there a constraint on n? The simple answer is no. Okay, because I can have any number of positive operators, you know, which can satisfy this requirement. Okay, and which sum to identity. Okay, but you can talk about some optimal sets. Okay, in particular, you can put a constraint that the EIs must be rank 1 operators. Okay, so think of these EIs as corresponding to a rank 1 operator, of course, can simply be written as the projector onto some pure state phi, right? Now, the difference between what the projective measurement does and what this kind of a rank 1 POVM does is that the rank 1 POVM need not be orthogonal. Okay, this need not be orthogonal. Since this need not be orthogonal, you see that you're no longer constrained by n should be d. No. Do you understand? So even if I put a constraint that the EIs must be rank 1 operators, because these rank 1 operators need not be orthogonal, there is nothing that dictates that I need D, right? So the first thing to note is the very specialized case where these are rank 1 and orthogonal, then n is indeed equal to D. So typically people take D to be a lower bound on n, where D is the dimension of your quantum space. Okay. Now, if you further put in another constraint, which says that these must be, so the other kind of constraint you can put is that the EIs must be linearly independent. Okay, there must be a set of linearly independent positive matrices, right? That's another constraint you can put. So in that case, yeah, write that separately. So typically in a two-dimensional Hilbert space, you will need a POVM to have at least 2 elements, right? That much is clear, right? However, in higher dimensions also, right, you can always construct 2 outcome POVMs, right? So even this D being a lower bound is not very, you know, it's not a very sacred lower bound. It's just that if you express it in terms of these rank 1 operators, well, then you need at least D of them because when they're orthogonal is the optimal sort of number, but then you allow for them to be non-orthogonal as well. And so you can have anything which is D or greater, okay? The other constraint that you can put is that the EIs must be independent, okay? So then you can, this then leads to the question of how many linearly independent operators can I have on a D-dimensional Hilbert space? Anybody know the answer already, or have you thought about it?
D square.
Indeed. Good. Well, the answer is D squared. Basically, this is the dimension of the space of matrices on the vector space. right? We've seen this before. We've seen this, that if I write down a space, this is like the space of M D cross D C2, right? That is the space of complex D cross D matrices, and a basis that spans this must have, or a set of linearly independent operators, you can have at most D squared of them, right? I mean, yeah, you cannot have more than D squared linearly independent operators. So then N actually becomes equal to D squared, right? So these are two markers, right? But these come because of certain constraints, right? If you don't put any of these constraints, then really N is unconstrained, right? It's only, you know, this that constrains it, and any set of operators that satisfies this is good, right? So people have analyzed things like this, where you put specific constraints, you ask, is there a minimal set that can represent every POVM? Can every POVM be written in some way, and so on and so forth? So these are all sort of deeper questions which get into measurement theory, you know, but yeah, I can give you some references if you're interested in this subject. Okay. I hope that answers your question.
Yes.
Okay.
Yes, thank you.
Okay, so let's move on to this distinguishing orthogonal states question. And I wanted to show you a simple proof. So the statement that I wanted to prove is that non-orthogonal quantum states cannot be distinguished perfectly. Okay, and this holds no matter whether the measurements you consider are POVMs or projections, right? So this is not just a statement that holds for projections; it holds for even when you include the class of POVMs, right? And this then will tie back to the example that we did of this two-party game with 0 and plus, where you had to add the third operator, right, which gave you a certain probability of failure. Even though it didn't give you error, it gave you a certain probability of failure, right? Okay, so first let us note that, let's first note that if we had a set of orthogonal states, so I'm going to call these as psi1. So S is my set of orthogonal states, psi1, psi2, etc. Some psi n, okay, on a three-dimensional space. This can always be distinguished, right? So this set can always be distinguished perfectly. Why is that? Yes?
We can perform an orthogonal measurement.
Indeed. So we can define orthogonal projections, Pi, which are simply projections onto the ith state, right? Now it's possible that sum over I Pi, which is sum over I psi I, is not identity, okay? But because this is a set of orthogonal states, it has to be less than equal to identity, okay? So then you can define a Pn plus 1, which is identity minus sum over I psi I, okay? This is in case this does not complete the space, right? So then you can simply perform this projective measurement. Let me call this also a measurement M. So the optimal measurement, if you will, or say, yeah, perform the measurement M, which is this set of projectors P1, P2, etc., Pn plus 1, right? And then you know that this set of states can be distinguished perfectly, right? So you can always, so what does perfect distinguishability mean, right? So let me state that also, make that more precise. So perfect distinguishability if psi I is measured, right? Or if psi I is a state that is received, right? So let me say received, because remember we are sort of in this is received or input to the measurement device. So I'm thinking of a measurement device, right? Which is going to collapse you to one of this set of orthogonal projections. Now, if the input state is psi I, what must happen? Only the ith dial should, or the ith lights, you can think of this as a set of lights, then only the ith light must go on, and all the other lights must be off, right? It's a very sort of toy way of thinking about it. But the point is here, only one projector should have probability 1, and all the other projectors should have probability 0. That's what one means by a perfectly distinguishable scenario, right? So perfect distinguishability entails that then probability of I, right, which is now trace pi psi, right? The input is psi I. The probability of I in state psi is pi psi. Now the input is psi I itself. What is this now? Yes. What is this? 1 indeed. Yeah. So the point is, if the input is psi I, outcome I should be realized with probability 1. Okay.
I have questions.
Sure.
What will the projector be n+1 project into?
Yeah, good. So the n+1 projector, you realize, because again, this is a set of orthogonal projectors, identity minus that is again something that is orthogonal to all the psi i's. This is just like completing the basis. Okay. What I'm saying is, if I go back to a cartoon picture of my space, and I say that each psi I is carving out a separate non-overlapping part of the space. Let's say I have 4 of them, but there is this remaining space. But this remaining space is orthogonal, has no overlap to all the other psi i's.
Yes, so there might be many states here, not just one.
It doesn't matter. I just define one projection onto this entire space. Remember, I told you that the projection need not have rank 1. So this is some higher rank projector, which I have called P5. Okay. I don't care about what state is here, because that outcome is never going to be realized, you see. It's just a way for me to say that I have a valid measurement. Okay. Because it's going to give a valid probability distribution. Right?
Okay.
Is that clear? Yazid, I think, asked the question.
Yeah, clear. Thank you.
Yeah, sure. Okay, so note that this projector is orthogonal to all the psi i's. As Yazid pointed out, there could be several states in this orthogonal subspace, but this projector is a higher rank projector onto that space. That's all, right? And you see, this outcome is never going to be realized so long as my inputs are from this set of psi i's, right? So trace of the Pn+1 psi I, let me keep this cartoon figure as a reference, if you will, is always 0 for all I going from 1 to n, right? So the n+1th projector is never going to get activated, right? Because you will notice that this is identity minus sum over this. You can actually work this out. So this is a good exercise for you. So homework, please check this. Don't take my word for it. check this for the definition that we have of Pn plus 1. The fact that it is identity minus the sum of a set of orthogonal rank 1 projectors gives you this property. Okay, so please check this. Huh? Okay, so this is what perfect distinguishability means. If I input a particular state, then the index corresponding to that state must be realized with probability 1, and all other outcomes have probability 0. Okay, fine. This is what perfect distinguishability means. And we can always achieve perfect distinguishability if we have a set of orthogonal states. They need not even complete the space, right? They need not even form a basis. It could just be some set of 4 orthogonal states like this, which partition the space into non-overlapping parts. But there could be a big chunk of the space which they don't even explore. It doesn't matter. I can define a projector to complete the measurement just to make it a valid measurement, and then I still have a way to distinguish these states perfectly. So if you go back to the two-party game scenario, anytime Anita is going to send a set of orthogonal quantum states, the game is won every time by Bharat, because he can construct a projective measurement corresponding to that set of orthogonal states and always win the game. Okay, so this is the reason that orthogonal states are often thought to be classical states, classical quantum states, in the sense that they mimic the behavior of classical states, right? For classical states, you don't ask questions about distinctness, distinguishability, and all of that stuff, right? Every classical state is distinct. It's a distinct point in some function space. It's a distinct entity, right? Now, what about non-orthogonal states? How do we show this? So let's now go to proving this theorem on non-orthogonal states.
Hello.
Yeah. Yes.
Ma'am, the cartoon picture above M, the measurement, is it POVM or it is just a projective measurement?
This is a projective measurement, right?
So ma'am, I have a doubt with this projective measurement that suppose I have a general state, suppose I have an input state psi I, and I measure it with some projector because I don't know what is psi I, and suppose I choose PJ. So with that, probability will be 0, and I will get what will be the output state? Nothing.
No. You should not think of the measurement device as applying one projector each time. No. The measurement device, the mechanics of that is not something we are getting into. But like I said, think of this as some device with like a bunch of lights, right? And the light corresponding to a particular outcome glows when that outcome is realized. Okay? Think of this in a very classical way, like you have an instrument with a dial, right? And the dial says 1, 2, 3, 4, etc. up to n. Depending on what the input state is, every time the dial will point to a particular number, right? If the input state is 1, in this case, the dial will point to 1. If the input state is 2, the dial will point to 2. That's a perfectly distinguishing measurement. If it is not a perfect measurement, for every input state, again, the dial will point somewhere, but it may not be the correct outcome, right? If the state input is 1, and sometimes the dial points to 2, and sometimes the dial points to 1, then that's not a perfectly distinguishing measurement. There is a certain non-zero probability of the dial to point to 2, even when the input state is 1.
Yes.
Okay. That's why I said it's a cartoon picture. You're not going into the mechanics of it. I mean, you can. That's why I gave the example of the Stern-Gerlach, where you see every time you input a single particle state, it goes up or down on the screen. So the up or down on the screen are the two lights, if you will, right? So either the top part of the screen glows or the bottom part of the screen glows. If the top part glows, you have realized one outcome. If the bottom part glows, you have realized another outcome. It's not that you have to do separate experiments to realize the different outcomes. Is that clear?
Yes, but in that case, here we are considering that if that electrons coming in are in a particular particular quantum state says psi I, then every time a single light will glow.
Yeah, but if it's a superposition, then we saw all
Then
this
there
last
will
time.
be,
Right?
yes. Yes, yes.
If it's a
Okay,
superposition, then half the time it will be up, half the time it will be down.
okay.
Now I'm
Yes.
working backwards. I am giving you a set of orthogonal states and I'm saying, here is a measurement you can always construct for this set of orthogonal states, right? Which will every time tell you the correct answer. Okay, yeah, it's a kind of, I'm working backwards now, where I'm giving you the set of orthogonal states and I'm saying, here is a set of orthogonal states. Can you construct a measurement? The answer is yes. Now, for the non-orthogonal case, I'm just going to consider a two-state scenario, and this can be extended to the n-state scenario, but the argument comes out more nicely in the just with the two states, right? So consider a psi1. Consider two states, psi1 and psi2, that are non-orthogonal. Okay. So that means that this overlap is not zero. Okay. Now I'm going to prove by contradiction. Okay. So I'm now going to assume that there exists a measurement, and now I mean measurement in the most general sense, including POVMs. Okay. Possibly a POVM, right? With two measurement operators. When I say measurement operators, I mean those positive operators. So let me call them E1 and E2, okay? Such that if E1 is realized, okay, then trace, so this is the probability that state 1, okay, so this is the probability of outcome 1 in state psi1, right? So let me write this in words itself. So I'll say probability of outcome 1 in state psi1. And I think Jayendra is the one who asked me the question at the very beginning of class. This goes back to what we discussed at the end of last class, which I had not recorded the last 5 minutes, where I had worked out these probabilities for that example, right? So this is where it comes from. So let's say probability of outcome 1 in state psi1. What is that? That is trace E1 psi1 psi1, right? Which is nothing but this, right? Now this should be 1, right? If it's a perfectly distinguishable measurement, right? If these two states are perfectly distinguishable and this is the measurement that achieves that, then probability of outcome 1 in state psi1 should be 1, and probability of outcome 2 in state psi2 should be also 1. So this is when it's a perfectly, this is when that you say that they are perfectly distinguishable, right? So assume that there exists a measurement that perfectly distinguishes this, right? So such that psi1 and psi2 are perfectly distinguishable. So what that entails is this, right? The probability of outcome 1, if state psi1 is the input state, should be 1. And the probability of outcome 2, if the state psi2, so this should also be 1. So let me call these equations as star, okay? Both these equations. Now, recall that if this is to be a valid measurement, there has to be a completeness relation, right? So I need to have E1 plus E2 is identity, right? For it to be a valid measurement. Okay, then so since psi1 E1 psi1 is 1, this must imply that psi1 E2 psi1 is what?
0.
It should be 0, indeed. Now note that E1 is a positive operator, so I can write this as psi1 square root E2 times square root E2 psi1 is 0. Essentially, I can write this as the inner product of two states, rather as the norm of a particular state. And what is that particular state? It is square root E2 acting on psi1, right? So square root E2 psi1 should be 0, right? So this is what I arrive at based on the fact that psi1 E1 psi1 is 1 and E1 plus E2 should be identity. Okay, so let's keep this equation aside. So let me call this as equation 1. Now note that since psi1 and psi2 have a non-zero overlap, right? We can expand one in terms of the other, right? So we can write psi2 as some alpha times psi1 plus beta times psi1 perpendicular. Okay, so psi1 perpendicular is just some state orthogonal to psi1. Okay, so I can always expand psi2 in terms of psi1 plus some state that is orthogonal to psi1, right? So, but because psi2 is a normalized state, right? Now normalization implies that mod alpha square plus mod beta square must be 1. Okay, so let me call this equation 2. Now let's work out what is square root E2 acting on psi2. Remember, we saw that square root E2 acting on psi1 is 0. So now you see we'll arrive at a contradiction. So square root E2 acting on psi2 will be alpha times square root E2 acting on psi1, but that term goes away, plus beta times square root E2 acting on psi1 perpendicular, right? So this is beta times square root E2 acting on some state. But this is already a contradiction because remember that star implied that psi2 E2 psi2 must be 1, right? So now let's see if this is consistent with the star equation above. So now from this equation, what is this inner product? Like I said, this is nothing but the norm of this state, right? Which is square root E2 psi2, right? So what is this? This becomes, so can you use this equation 3 to tell me what this becomes? So this is
Mod beta square psi1 perpendicular E2 psi1 perpendicular.
Indeed, yeah, good. So there is a mod beta squared because you see, what do we have to do? We have to take the bra of this equation, right? So that will become, this will become a beta star, and then you have to multiply both parts. So let me write this below here itself. So this is beta star psi1 perpendicular square root E2, beta square root E2 psi1 perpendicular, right? So this becomes mod beta squared psi1 perpendicular E2 psi1 perpendicular, right? And now you can see that this should be something that is less than or equal to mod beta squared, because this quantity has to be less than or equal to 1. It is the expectation value of this operator in some state, some psi1 perpendicular state. But E2 being an operator that lies between 0 and identity, its expectation must lie between 0 and 1. This is what we saw earlier also. So this is something which is less than or equal to 1. So the product of that with beta squared must be less than equal to mod beta squared. But mod beta squared itself is less than 1, right? Because of this, right? So the bottom line is, if there is some non-zero beta here, rather if there is some non-zero alpha here, right? If beta is not 1, suppose psi2 and psi1 were orthogonal, then beta would be 1 essentially, because there is no alpha. There is no overlap of psi2 with psi1. But if beta is not 1, then you see a certain contradiction that the probability of outcome 2 in state psi2, which is what we defined as, which is what the probability rule tells you that this is what it should be. This turns out to be something less than 1, but this is a contradiction to what we had earlier. So this is then a contradiction. So this is, let's see, not consistent with star above, which was basically the definition of a perfectly distinguishable measurement. So we don't have a measurement that perfectly distinguishes psi1 and psi2. Okay, so there are two things that we used. Basically, psi1 is and psi2 have non-zero overlap, so you can expand one in terms of the other, right? And the fact that E1 and E2 must sum to identity, and they must lead to a perfect measurement. Actually, we don't even have to keep star. We can just start here and say, okay, if I have a measurement like this E1, E2, then it can't happen that both these probabilities are 1, right? I started by saying psi1, psi1, E2, psi1 should be 0, right? Because psi1, E1, psi1 should be 1. But then you end up with psi2, E2, psi2 not being 1, being something strictly less than 1, right? So is this idea clear? The statement and the proof of this? Yes, no, maybe?
Yes, ma'am.
Okay, so to go back to the example that we did the other day, and I guess I shall have to stop there. I wanted to introduce the idea of density operator today, but I'm not able to. Okay, so let's revisit the example that we did. And remember the zero error discrimination strategy. Was to construct these 3 POVMs. I don't know what I called them the last time, whether I called them M1 or E1. So anyway, I'll call them E1 now. So this was, one was a projection onto 1 with a factor, right? To make sure that, so let me just explain this idea again. So remember, in the case of orthogonal projectors, we could simply take, so if you go up to this example that I did here first, this general statement of psi1, these psi i's, right? So I said that sum over I, psi I, when I take these projectors, this is always guaranteed to be less than identity because they are orthogonal projectors, right? I hope everyone understands this statement because this is a significant statement, okay? And one way to understand it is by this cartoon picture. So each projection P1, P2, P3, P4 is projecting you to non-overlapping parts of your Hilbert space. So if I sum up a bunch of such orthogonal projectors, either it should cover the space or it should be something that is less than the full space. It cannot be greater than identity. Okay? But when I have overlapping projectors, when I have projectors like this, 1, 1 and plus plus, then this sum, okay, which is a projection onto 1 plus a projection onto plus, this is not less than identity in general. Okay. Because you can imagine that I have this two-dimensional space. One, let's say, bifurcates the space, right? But plus is something completely different, which has an overlap with one also, right? And this sum of these two, if I put them together, can in general exceed the full space. Okay, so this is not a orthogonal partitioning of the space. So there is no reason that this sum should be less than identity. In fact, this sum will be greater than identity. Oh, by the way, this should be the minus state. Sorry. Yeah. So anyway, it doesn't matter. Any state which has overlap with one. So that is the reason that I need this normalization things here, right? So that is the reason I cannot, in the second case where I had psi1 and psi2, which are non-orthogonal, I cannot do the strategy of simply taking psi1, psi1, psi2, psi2. That will not, I mean, together I cannot complete it to even form a measurement, a valid measurement, whether projective or POV. Okay. All right. So with that reminder of why we need this square root 2 by 1 plus square root 2, recall that there is a third operator now, which is identity minus E1 minus E2. Right? Okay, so now we can work out these probabilities, right? So what is the probability of outcome 1, right? So remember E1, I'm associating this with E1, right? If the input state is 0. So this you can see is simply trace E1 0 0, right? And this is indeed 0. Okay. But what is the probability of outcome 1 if input state is plus? This is trace E1 plus plus, okay, which is root 2 by 1 plus root 2, okay, plus remember E1 is a projection on 1, so this is 1 plus 1 mod squared, right? So this basically gives me 1 over root 2, 1 plus root, which is much less than 1. So this is exactly what this proof captures, right? That if you make one of them to have probability 0, the other probability cannot be made 1. Okay? If the two states are non-orthogonal. So in this example, what we are trying to work out is a different kind of strategy, which is we're saying, I'm not going to aim for probability 1, rather I'm going to aim for probability 0, so that I don't make a mistake. So that if the input state is 0, I will never get outcome 1. Okay, so if I get outcome 1, I know for sure that it is not input state 0. Okay, similarly, you can see that probability of outcome 0, outcome 2, if input state is plus, is 0, and probability of outcome 2, if input state is 0, will again be something less than 1. It will not be something that is equal to 1. Okay, I leave it to you to work out these probabilities. And the residual probability, right, which is the remainder from 1, is what gets covered by E3. Right? That's literally what we're doing here. It's identity minus E1 plus E2. It's a residue from 1, right? Of the residual probability is all sitting here, and that is what we would call a probability of failure. Because these are the cases where Bharat is going to throw up his hands and say, I can't give you an answer. I give up. I concede. But if Bharat gets outcome 1 or 2, he knows for sure which state it is not. So then he knows for sure which state it is. Okay. So I hope this has given you some idea of what the zero error discrimination strategy is and why it is still not a perfect distinguishing strategy, and why you can never have a perfect distinguishing strategy for a pair of non-orthogonal states. Okay, questions? Okay, so if there are no more questions, then we meet tomorrow, and I'll introduce the idea of a density operator tomorrow. Okay.
Yes, ma'am. Thank you.
All right, see you all tomorrow.